Hello everyone. Welcome to the second lecture on convex optimization. So unfortunately, in the last class we could not record the lecture due to some technical difficulties. So this is an offline recording of the second lecture. So without further ado, let's start. So a quick recap. In the last class, we saw what is an optimization problem, the framework of an optimization problem, right? So we saw that this is in an optimization problem, we are minimizing an objective function f0x subject to certain constraint. Okay, so this optimization function, for example, in let's take R, let's say x is in R, and we have a function like this. Okay, and we are minimizing it. So if you minimize this function, what will happen? So the solver will find, or we know that this is the point x star, right? Which minimizes this function f0x. But now we are saying that it's not only just minimizing this function f0x, we have to satisfy certain constraint f(i)x less than bi. So there are m different constraints for various values of I. For example, f1x less than b1, f2x less than b2, like that. So what will happen here? For example, in this problem, now we are saying that it's not just minimizing f0x. We while minimizing, we have to, for example, we have to satisfy this constraint that x belongs to this set. Okay, so in this case, now we know that x0 is not, this x star is not the minimum value, or this x star is not the value that minimizes f0, the function. Now the new minimum point will be this x dash, right? So what is the point here? The point is that when you add constraint, it is not only minimizing, it's not just minimizing the function. Now you are saying, you are asking the solver that you cannot minimize our entire real line, but you have to constrain your search of minimizing over this set, right? So essentially that means when you add constraint, the solution can change. Okay, so for example, you add constraint, you are saying that my new constraint is this, then the solution is different. If the constraint is this, the solution is different. So this is what we saw. Okay, so now we also saw that, so provided an optimization problem, it is not guaranteed that in general we can solve the problem. There can be some problem which can be solved. There are some other problem which is very difficult to solve, or which cannot be solved at all. So then in that following that discussion, we saw that an optimization problem can be categorized into two classes. One is convex optimization problem, other one is non-convex optimization problem. So we now know that, roughly we know that if the problem is convex, we are happy. It is well studied class of problem, and there are some algorithms which we may find to solve, or a closed form solution if you are lucky, or essentially the problem can be solved. Uh, but if it's a non-convex problem, then we are sad actually, because it is very difficult to solve. Then sometimes you may be able to solve it by going for certain compromises or certain relaxation. But in general, if you have a non-convex problem, it is very difficult to solve. Now we said this very roughly in last class. Now we are going to study in detail how can you know that provided a optimization problem, whether this is convex or not. So in the last class, we also saw that. So an optimization problem is convex if both the objective function and the constraints um, objective function is convex and the constraint set are convex. So what does that mean? We roughly saw that, for example, if the function is having a shape like this, it is not convex. And if the function is something like this, convex. So this is very informal way of telling this, but we will see in detail how do you formally state, how do you formally identify whether the function is convex or not. Also, we saw that in the last class, the constraint set. Why do you say constraint set? Because when you apply constraints like this, it points to a set, right? For example, here, uh, uh, let's say we are saying that x is less than a and greater than b, right? The moment you say that, you have a set between b and a, right? So this is called constraint set. So then we have a constraint set. Here, if you see, we have a function to minimize. This is the function, and then this is in R2. So you have x1 here, x2 here. Now you are putting a constraint. What is a constraint? You are saying that I cannot search over all the R2. This is not possible, but I have to search in this constraint set. Okay. So now the question is, how do you know that the constraint set is convex or not? So last class we just say that, okay, if you have a set something like this shape, this is convex, but this is not convex. So we didn't go into detail. We saw that we said that, okay, how do you know the set is convex? Take 2 points and in the set and draw a line between, draw a line connecting those points. So if those points lies within the set, that is convex. So here, if you take any 2 points and draw a line, that will be within the set. But in this set, if you take these 2 points and draw a line, that this part is not in within the set. So that means this set is convex and this is non-convex, right? Now, in this class, we will formally we will define convexity and non-convexity more formally. Okay, so let's get started. Yeah. So this class, okay. Before that, we already said that in this course we will be following slides from Professor Boyd. So and we will also discuss some topics from his text. Basically, these slides are prepared from his textbook. So we give courtesy to Stephen Boyd for this lecture. Yeah, so this class we will see what is a convex set, how do you define that, what are the properties, what are the operations that preserve convexity. Okay. Okay. At this point, yeah, now we start with affine set. Yeah, at this point, it is useful to study various combinations. Okay, so we study different combinations. Sorry. So let's first see what is a linear combination. Let's say we have different points, vector x1, x2, like that. Okay. Now, a linear combination is something like weighted sum of xi's, okay, such that theta I is a real number. So here there is no restrictions on theta I. We just say that it should belongs to R, but it can be any value. It can be positive, negative, and all theta I can be equal, not equal, anything. Theta I can be zero, anything. So then let's take a case. Let's try to understand what is happening here. So let's take a case. Yeah, let's assume that let's consider R2. So we have two, sorry, and let's consider 2 points in R2. For example, this is X1 and this is X2. So now what happens when we take a linear combination of these guys? So for example, let's assume theta 1 equal to 1 and theta 2 also equal to 1. That means you are just adding x1 and x2. Okay, so this is the vector x1 and this is the vector x2. When you add these two, you will get something like this, right? And then again, let's say yeah, theta 1, and for example theta 1 is half, theta 2 is half. Then if you add, you will get this vector, right? So what happens, like let's assume, or let's consider all the possible values of theta I in R. Okay, in that case what happens, for example, if you add this guy, so when you add theta x1 and x2, you got this. Then if you add these two guys, you will get something like this. For example, if you take a negative value here, if you add, you will get something like this. And so if you take all the possible combination, you will get many points. And if you consider all such possible combination, what you will be getting is the entire R2, right? So that will span the entire R2. So we can say that linear span of x1 and x2 is R2. So remember, I am considering an example in R2, okay, and also just assume that here we assume that x1 and x2 are linearly dependent. So if you take R1, x1 like this and x2 like this will not span, right? So here we make this assumption. So be clear on that. So on the for all the following discussion, we assume that x's are linearly independent. So this is what a linear combination. Now we go to next combination, which is an affine combination. Okay, so what is an affine combination? It is again a weighted sum, theta I xi. Theta I is in R, and now there is a second constraint, okay, which is I cannot take any set of theta I. There should be a constraint. That means if I add theta I, that should be 1. Basically, theta I add up to 1, right? So now again we will see what is happening in what is happening here. So let's again take two vectors, x1, x2. They are linearly independent, and so if I take theta 1 equal to 0.5, then theta 2 equal to So if you add these two guys with these values of theta, you will get this. Okay. Now you can try with the various values of theta. For example, if you take theta 1 to be 0 and theta 2 to be 1, then you will get x2. If you take theta 2 to be 0 and theta 1 to be 1, then you will get x1. And as you varying theta i's with this constraint, you will get different points like this, and basically it will be a line passing through x1 and x2. Okay, so now we can say that affine combination or affine span of the points x1 and x2 is the line passing through x1 and x2, right? So these are vectors actually. Yeah. Now the third one, convex combination. So what is a convex combination? So it is a weighted sum of xi's. Weights are theta I, and theta I as usual belongs to R. And here again we have the same constraint, theta I should add to 1, and we have an additional constraint here, theta I should belongs to the interval 0, 1. So I cannot take a theta I as something like a 1.5 or something. It has to stay within 0 and 1. Okay, here for affine combination, we should even take a negative value of theta. For example, this is x1, and let's take theta 2 to be negative 1, then that will be, sorry, then that will be a vector of this, and if you add these two guys, you will get something. If you add these two guys, you will get some points here, right? It will again on this line, but here you cannot take a negative value or a value like 2 or 3. It has to be between 0 and 1. So what will happen here? Let's again consider the same vectors x1 and x2. So now as we said, if you take for example theta 1 equal to 0, you will get this point. Theta 2 to be 0, you will get this point. If you take 0.5, you will get this point. And if you vary in between 0 and 1 the values of theta and take all the combination, you will get a line segment between x1 and x2. So it's not the entire line between x1 and x2, it is the line segment between x1 and x2. So that's the difference between an affine combination and convex combination. So we can say that convex span, I don't know whether we can formally write a word convex span, so I'm putting this in. Like I am using this notation, convex span of x1 and x2, but you know what I mean. X1 and x2 is the line segment between x1, vector x1 and vector x2. Okay. Okay. There is a fourth category of combination, which is called a conic combination. Let's see what it is. It is again weighted sum of xi, but now the constraint is that theta I has to be greater than or equal to 0. Okay, we don't have this constraint of adding up to unity. We only have the constraint which says that the weight has to be non-negative. Okay, here what happens if you examine the span of two vectors. For the same vector, we are taking x1 and x2. So now we are saying that any weights which are non-negative. So again, if you take theta 1 and theta 2 to be 1, it will be this. And theta, for example, if you take theta 1 and theta to be half, you will get this one. And if you take theta 1 theta to be 0 and just take the other guy, for example, theta 1 to be 1, you will get. And if you will also get, for example, theta 1 to be 2 and theta 2 to be 0, then you will get this point. And you can, similarly, you can get points like this, points here, 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 like this. And basically, this will be a cone shape between the vector x1 and x2. So you will have something like, you will have this region, this conic region, which extends to infinity. So this is giving a cone kind of shape. That's why we are calling this combination as conic combination. Okay, so then we can write that conic span, again this may not be a formal word, conic span of x1 and x2 is, so this is called a convex cone. Convex cone is the convex cone. So let's call this as C, this cone, convex cone C. Okay. Okay, now we saw different combinations, linear, affine, convex, and conic combinations. Now with these definitions, we will be moving forward to see what is an affine set and different categories of set. So first, let's see what is an affine set. So we already know what is a affine combination, right? So affine set is defined as, affine set is a set which contains the line passing through any two distinct points in the set. Okay, so for example, here we have x1 and x2. Yeah, so I am forming a new line x such that it is defined by theta x1 plus 1 minus theta x2. So if you notice, it is similar to our previous discussion. This is an affine combination because if you add theta plus 1 minus theta, this will be 1. So this is equivalent to our previous discussion where we say that the weighing coefficient should add to 1, right? So here, this is an affine combination. Yeah, so now let's consider a set, for example, this line, and you pick any 2 points, x1 and x2. When theta equal to 1, you will get this point because then 1 minus theta is 0, so that is x1 itself. When theta equal to 0, you will get this point. And for example, theta equal to 0.6, you will get this point. And as you keep on varying theta, you will get a line passing through this line, right? I mean, line passing through these 2 points. So if you consider this line, that is an affine set because any 2 points in this line, if you take and then the set contains the line through that point. To make it clear, let's take a new set consider a new set, for example, like this. So we have an R2, X is in R2, and I am saying that I have a set C, which is basically this strip. Okay, this is my set C. Is this set affine? No, because if you take, for example, 2 points in the set like this, uh, x1 and x2, of course, it contains the line through this point. But what happens if you take 2 points like this, x1 and x2 here? The line through this point is this one, but this line is not contained in this set. Only a part of this line is in the set. So this is not an affine set. Okay, so what are the examples of an affine set? For example, here a line itself is an affine set. And another example is solution set of linear equation ax equal to b. Why? Because let's see whether this set is affine or not. Let's check it out. So let's call this set C. Set as C. C is defined as x, such that x is the solution of ax equal to b, right? So let's take 2 points. So what we want to check is you take any 2 points, and the set should contain the line passing through those points. So then, yeah, so take 2 points, x1 and x2. Yeah, so x1 belongs to C. Let's assume that these 2 points are in C. All right. Now we have to take an affine combination of this. Let's say no point y is an affine combination theta x1 plus 1 minus theta x2. So as you vary theta, you will get the line passing through x1 and x2, right? So if y is in this set, then we can say that the line passing through x1 and x2 is in this set. So how do we check it? So we are observing whether a of y equal to b, right? So why? Because the set, if a of y is equal to b, then it satisfies this equation here, and then y is in the set C. So let's see what is a of y. A of y equal to a into theta x1 plus 1 minus theta x2, which is equal to theta into ax1 is b, right? Because x1 is in set C, that means ax1 equal to b, which implies ax2 equal to b. So the theta into ax1, which is equal to b, plus ax2, which is equal to again b from here, minus theta into ax2, which is again b. So this is equal to b. So now we saw that y is, which implies y belongs to C. That means we are saying that the affine combination of x1 and x2, which gives the line passing through x1 and x2, is in the set C. So set C is affine. So that's how we prove the solution set of linear equation is affine. Yeah, so this is a useful concept, the affine set. The next concept is convex set. So remember, we are investigating the properties of set here. Why? Because initially we saw that the constraints gives to a set, and now we have to see whether that set is convex or not to understand whether our problem is easy or not, right? So now we are not yet at the point convex set. We saw what is an affine set. Now next concept is what is a convex set. So it is something similar. The definition is something similar. Instead of affine combination, we consider here a convex combination. Okay, so convex set is, now we can guess what it is. Convex set is a set. It is a set containing the line segment between any 2 points in the set. So how do you define the line segment between 2 points? Using a convex combination. So now you have x equal to theta x1 plus 1 minus theta x2. Now you know that if you add theta plus 1 minus theta, that equal to 1. Okay, this satisfies first constraints of the converse combination. And the next constraint is theta has to be between 0 and 1. Okay, so if you apply these two constraints, then this combination is called converse combination, which gives the line segment between x1 and x2, which we already saw, right? So then in a set, if you pick any 2 points, and then you can, if you can verify that the line segment between those 2 points lies within the set itself, then that set is convex set. For example, here if you pick this set, and yeah, so let's take 2 points from this, and if you draw a line between those points, that is within the set. If you take a line between these 2 points, that is within the set, right? Here, that is within the set. But what happens for this set? So this is a convex set. What happens for this set? If you take two lines here, yes, of course, the lines between that points is in the set. But what happens if you take these 2 points, you draw the line, but this region is not, this part of the line segment is not within the set, right? So for a set to be convex, the line segment between all the any 2 points of the set has to be within the set, right? So here that is not satisfying, so this is a non-convex. Now what happens if you take this set, the third set? So take 2 points, the line segment between those points is in the set here, but here we can see that there is a break in the boundary, and these points between those, for example, if you pick these 2 points, and the line between, I mean the line segment between these points is not the part of set, because there is a break in the boundary, right? So because of that reason, since this part is not this line segment is not contained in the set, this is a non-convex set. All right. So of course you can think about any kind of sets and verify this. For example, if you take this set, this is non-convex. Why? Because you pick 2 points here, and if you draw the line between those points, that I mean the line segment between those 2 points, that part, this region is not falling within the set, so this is non-convex. So let's go back to the previous example here. Is this set convex or not? You take any 2 points, draw the line segment between draw the line between those 2 points, that is within the set, right? Here also, if you consider these 2 points, the line segment is this, so that is within the set. Okay, so this set is a convex set. This is convex set, but this is not an affine set, because the entire line passing through these 2 points are not in the set, so that is not an affine set, but this is a convex set. So we saw what is a convex set. What is a convex set? It is a set. A set is said to be convex if you pick any 2 points and take the convex combination. That means a line segment between those 2 points, and that line segment should contained within the set. Then the set is called a convex set. Okay, so we saw what is a convex set. Next is convex combination and convex hull. So we already saw what is a convex combination, right? This is a weighted sum where theta has to be the weight adds up to 1, right? And theta I should be greater than 0. Okay, so we in the definition that we used before, here we said, right, theta has to be between 0 and 1, but these are equivalent definition. By you can also we can also say that theta I should be greater than 1, because when theta are to be 1, theta, if you say theta should be greater, theta is greater than or equal to 0, that means theta I has to be between 0 and 1, right? This is understood. So you can state the definition of converse combination in both the way. Yeah, so with this definition, you know what is a converse combination, right? Uh, yeah, then uh, what is a converse hull? So it is sort of yeah, I can say this. Uh, for example, you consider a set here C. So this is our initial set. Let's take a set C here. So this is set C. Is this set convex? No, right? Because the line segment between 2 points here, this region is not within the set C. So convex hull is a concept where you are forming a convex set, a closest convex set from this. So what you have to do is the easiest way to add this region, right? So you add all those regions, right? Add like this, and now the new set C is convex. Let's call this as C dash. C dash is convex, whereas C was not convex, right? So how do you form this convex hull? Set of all convex combinations of points in S. That's what we did. This set was not part of the original set. Sorry, this line segment was not part of the original set. Then we add that. Then now, if you take this new set, all the convex combinations are within the set, right? So this is sort of, for example, you can visualize this as in 2D. You can visualize as like taking a rubber band, here and putting it like this, right? When you put a rubber band, it will take this form, right? If you take another example, let's consider this set here. When you put a rubber band, what happens? That will be, let's take a different color here. That will be something like this, right? So that is the convex hull here. Convex hull of the set C. Okay. So that's the convex hull. It's a set of all convex combination of points within the set. Now, if what happens if you consider this? Let's take this set. So this is, we know that this is already a convex set, right? So let's call this set as S. So this is already a convex set. Now, even if you form the convex hull, it will be that set itself, because you take all the points, include the line segment between those points, right? You take these 2 points, and then finally you get the set itself. So convex hull of a convex set is that set itself. Yeah.